Okay, so hi everyone. My name is Olivier, or Oliver if you prefer, and I'm a third year PhD student at the University of Toronto. And I'm basically extremely passionate about planetary navigation. And today I just wanted to basically share with you, as part of the Science Odyssey event, some details behind planetary navigation. Often in the news, whenever we talk about robots driving on the surface of another planet, like the one we see right now on the screen, we often talk about the main objectives and the science behind these missions, but there's also a lot of engineering that goes on and behind the scenes. And today I wanted to talk about one of these engineering challenges, which is to drive on the surface of another planet. So today's presentation, the way it's going to work is it'll last about 45 minutes. And during those 45 minutes, feel free, if you have any questions, feel free to write them in the chat. Oh, I see there's already a couple of people writing some comments in the chat. That's great. And after the presentation, I'll spend about 15-20 minutes answering these questions if there's any, and that will conclude the event. So without further ado, I'll just get started. Okay, so first I thought I'd mention a couple things about me. I'm as I mentioned, a third year PhD student at the University of Toronto, and I'm studying aerospace engineering and planetary robotics. And right before that, I completed my Bachelor's of Engineering in Mechanical Engineering, actually, at McGill University. I also completed a minor in Geology. Also, something I've been extremely lucky to do over the past couple of years is a few internships and research visits at NASA's Jet Propulsion Laboratory, and that's NASA's main Mars rover center. They do a lot of robotics and a lot of spacecraft design, and I've been lucky enough to go there a couple times for a total of about 2 years. And on that picture right here, we can see the Perseverance rover. And Perseverance is the latest rover sent by NASA. And it's a bit crazy to think that I was right there a couple meters away from that rover in early 2020, and now it's several millions of kilometers away on the Martian surface exploring. That's just great. So whenever I talk about planetary rovers, I'd love to give a bit of background of where we're coming from as humans exploring the surface of Mars with robots driving around, or at least moving around. So let me just move that around. So something that not many people know is that the Soviet Union was actually the one to, they were the first ones to try to explore the surface of Mars with a mobile robot. They had this little Prop M robot, but unfortunately it did not work out very well. After the Mars 3 mission, which was the main mission carrying this little robot, landed, the lander failed a couple seconds after landing. So the little robot was never deployed to the surface. But afterwards, America sort of took over, and several years later, Sojourner was a technology demonstration to show that it was viable to have rovers that were self-sustaining, driving on the Martian surface and collect scientific data. And this paved the way to bigger rovers, like the ones Spirit and Opportunity. These were twin rovers. They were solar powered. And one of them, Opportunity, actually lasted about 14 years. And the initial mission length was intended to only be about 3 months. So that was a huge, huge success. Today, there are 2 rovers that are active, and these 2 rovers here. At first, they look alike. They look very similar, but the science package and their science objectives are wildly different. They have a totally different set of instruments on board. Curiosity landed on Mars back in 2012. And Perseverance landed there back in February. You might have heard of that mission actually in the news. It was a smashing success, and we even see a little his little buddy that he or she brought along, the Mars helicopter right there in the image. Also, I think this picture here gives a lot of perspective on the size of these robots and how much we've progressed in terms of robots sent to Mars, from the little Sojourner, which is literally has the size of a microwave oven, all the way to Curiosity and Perseverance, which has a similar form factor, which literally have a similar size to a small car. So this is probably my favorite picture assembled together of the Curiosity rover mission. And it basically shows the Curiosity rover on the surface of Mars. One of the things I'd like to show you today is to not only tell you how the rovers drive autonomously on the surface of Mars, but also what are some of the dangers on Mars and what are some of the challenges to communicate with these rovers. And this picture here paints it just shows how diverse the Martian environment is. And so just to get started, we see that the Martian terrain can be very sandy. We see some loose soil here. We can also have very compact soil, like some dirt. We call it regolith. There's also exposed rocks that the rover has to drive over. And the Martian environment is also extremely dusty. And we see a bit of that dust deposited on the rover. Also, things that we don't really see is that the Martian environment can be extremely cold. Where Curiosity is, and of course that depends on what time of the day it is, where the robot is on the Martian surface, and also what season it is, because Mars also has seasons. But the temperature is generally very cold, close to -50, -60 degrees. During the summer, if you're at the right location at the right time of the day, it can go even above 0 degrees, but generally it's much colder than that. And the nights can go down to -70, -80, -90 degrees Celsius. And some places on Mars even will go way below -100 degrees Celsius. So Mars in general is extremely cold, and robots have to survive this very cold environment. Also, Curiosity and all the other robots are subject to a lot of radiation bombarding Mars. And something that we don't see in that picture is that the Martian surface, actually the gravity on Mars is about 38% of what it is on Earth. So that means that it's a little more than 1/3 of it, which means that if you were to stand on the surface of Mars, you should be able to actually jump a little less than 3 times as high as you would on Earth, which is pretty cool. But for robots, that means that there's less gravity pulling them down, which means that they'll have less traction driving around on Mars, so they could slip a bit more. But that gravity also affects all of the rocks and all of the dirt around them. So that's something extremely important to take into consideration when these robots try to cross this very diverse environment. Also, you might have noticed Curiosity has sustained quite extensive wheel damage since the beginning of the mission. We'll talk about that a little later. But this issue is under control right now. But the gist of it was that the Martian environment also is pretty windy, and bringing dust, basically having dust being blown on the Martian surface, will erode away some of the rocks that are exposed on the surface and sharpen them very sharp. And some of them actually damage the wheels of the rover. But we'll go into some deeper details about this damage a little later on. Also, rovers have to contend with very slippery terrain. When it's very sandy, we always have to be cautious because you want to make sure you don't get the rover stuck in some loose sand, because there's no one on Mars right now to help these rovers out. So if they ever get stuck in sand, they have to unstuck themselves, basically. They have to get out of it by themselves. Here's an example here. There was this one sand dune. People were very worried about it, but in the end, the rover was able to cross it pretty well. There's this valley here, also called Hidden Valley, that people thought that the rover should be able to traverse, and in the end, Curiosity was not able to traverse it, and they had to backtrack, and the rover almost got stuck there. So that's always a reminder that Mars is not always easy to drive on. So now that you have a bit of knowledge about what's difficult about the Martian environment, it's now time to talk about how to get rovers to drive in this environment. And this is the big picture of how we go about getting rovers to drive on the surface of Mars. Basically, this happens in 2 big steps. The first step is you'll have teams of human operators on Earth, especially at the Jet Propulsion Laboratory, but also at different centers and research centers and universities around the world, working together to decide what the rovers should do on the surface and put together a list of tasks that they should accomplish during the day. And then every day they'll send this list of tasks to the rovers, and the rovers will be on their own and they'll have to execute all these tasks. In our case, we're interested in talking about how these rovers will have to, how they drive around basically. At the end of their workday, the rovers will have collected probably a lot of data, a lot of pictures, and they will send all this data back to Earth, and the human operators will take this data into account, and this will help them prepare the list of activities to accomplish during the next day, and so on. So this loop just keeps going and going and going until the end of the mission. All right, let me just take a quick sip of water. Okay, I think we're doing good all the time. So the first part of the presentation will actually talk about how humans coordinate together and how difficult it is for them to communicate and command the rover every single day. The first thing that the humans will do is to perform strategic planning. And what essentially strategic planning is they will look at very high resolution orbital images of the Martian surface, and they will basically work with scientists, and engineers and scientists will work together to decide where the rover should go. So what are the scientifically interesting bits to look at? Maybe there's some interesting geology, chemistry we want to investigate, some specific minerals that we've identified that we want to learn more about. So these waypoints will be laid out on the map, and then engineers and scientists again will work together to try to draft a trajectory that the rover should follow over the next couple of weeks. These very high resolution orbital images can basically be collected with orbiters. So basically there are satellites in orbit around Mars. Some of them have very high resolution cameras. One of them is the Mars Reconnaissance Orbiter, and it carries this very high resolution camera called HiRISE. So I just realized, and NASA really loves acronyms, by the way. So if you ever read about NASA and rovers and spacecrafts, you'll see that there are lots of acronyms, and I forgot to remove this one here. I think HiRISE stands for High Resolution Imaging Science Experiment or something like that. It's essentially a very big camera. And here's a picture of Jezero Crater. Jezero Crater is the place that the Curiosity rover is currently exploring. Curiosity is the rover that landed a couple years back then in 2012. And this camera, HiRISE, took a very high resolution picture of this little area here, which is the little red area. And that strip was actually, I've magnified it on the right here. HiRISE can only have the middle, the center part of these images in color. The rest are just in black and white, unfortunately. But I just want to give you an idea of how high resolution these images are. So if we zoom in on that yellow rectangle, we can already start to make out some of the very big dark sand dunes around. If we keep zooming in, we start to make out some of the surface features that were carved away through erosion, through sand and water erosion a very long time ago. And if we zoom in here, you'll probably start noticing something. This image was actually taken when the Curiosity rover was already on the surface, and we can see it here. So you have an orbiter that's several hundreds of kilometers above the Martian surface, and it can take pictures that are so high in resolution that you can see objects that are just barely 2 meters long on the Martian surface, which is just mind-blowing in my opinion. And these images can reach about, I think, 25 centimeters per pixel, which is extremely high. It's ridiculously high. It's great. We even see some tracks that the rover, where the rover drove in order to get to that location. So basically the rover drove down here, did a couple point turns, turned around, and then kept going. Human operators back on Earth will actually make use of this very highly technological, these 3D anaglyph red and blue glasses to have a bit of a perception of what are the depth to different distance that are being either imaged by the rover on Earth, but also by orbiters above the Martian surface like we just saw. The same scenery that we saw is actually, I have an anaglyph here. So if you have a pair of red and blue glasses, if you want to look at this presentation again a little later, just take a look at it, then you'll have a sense for what the elevation is in that region. That here the elevation was very exaggerated. It's not as much extreme as you would see it here, but it still gives you a bit more of an idea what the rover has to contend with on the Martian surface at that location. Then once we've identified all the locations we want to visit in the next couple of weeks, we'll do what we call tactical planning. And tactical planning essentially consists in setting exactly a detailed list of what are the different activities that the rover will have to accomplish the following day. So we get into very nitty-gritty detail. And here's an example from that was put together by Evan Hilgeman. I'm butchering his name now, but there's this very interesting Medium articles that goes into a bit more details as to how that works. But essentially, humans will look at the imagery that the rover collected over the past couple of days, and they'll try to regenerate as best as they can the 3D environment around the rover based on these images, and prepare a list of commands to tell the rover what to do. In that case, to drive around, they'll tell the rover to go straight ahead, then turn right and keep going. The imagery returned by the rover is also extremely useful, not only to know where to drive, but also to try to estimate where the rover is on the Martian surface. So I chose that specific image, actually it's a panorama of images, because this was taken at the exact same place that we looked at a little bit earlier. And you probably already saw, but this little step here, these rocks are actually visible right here. And this little mountain or hill, whatever you want to call it, is actually this little mountain here. So in the event where we have an image, but we don't know exactly where the rover is, with very high accuracy, we can use the surface imagery to basically reconstruct where every features that the rover sees are on the orbital map, and try to have a better estimate of where the rover is. All right, so now we've decided where we want to go in the next couple of weeks. We have a plan ready to tell the rover what to do tomorrow. It's now time to communicate with it. To do so, humans will make use of the Deep Space Network. And that's a big network of antennas all around the world that is managed also at NASA's Jet Propulsion Laboratory in a place they call the center of the universe. And there are basically 3 different locations where there are antennas supporting the Deep Space Network. There are some in Goldstone, California, some in Madrid, Spain, and some in Canberra, Australia. And why these specific locations is that if you were to look at planet Earth from the top down, looking down at the North Pole, like how it's laid out here, these antennas are actually separated by about 120 degrees all around the world. They're basically at more or less equal distance if you follow the longitudes along the Earth. And that's very useful because regardless of what the orientation of the Earth is, there'll always be at least one station able to communicate with Mars, because it will be facing it. So when we have to send commands to the rover, we'll make use of sometimes some of the orbiters that are already in orbit around Mars. When we send the commands, it'll take between 3 and 23 minutes to just because the Earth and Mars, at some point as they turn around the sun, on their orbit around the sun, they can be pretty close together, but also sometimes they can be very far apart together. So that's why that changes all the time. So we'll send the commands to the rover this way. Once the rover is done collecting data and images, it'll communicate them to its little friend, the orbiter in orbit. And this orbiter will basically send back this data. Now there's a lot of delays. It takes between 3 and 23 minutes, so it's impossible for us to control in real time the rover on Mars. So because of that, humans will typically we'll communicate with it once a day, just send it all the instructions it has to follow of all the activities it has to accomplish. And there's also a little challenge here. It's pretty interesting. So basically, if we have a cycle of day and night of where the rover is on Mars, we want to keep the rover working during the day, because that's when there's sunlight, that's when it's much warmer than at night, so that's when we want the rover to work. So that means that human operators will have to work when it's nighttime on Mars, so that the rovers at the end of their day will be able to send back all the data, will be able to downlink that from the rover. Humans will be able to work during the Martian night, and uplink the whole new set of activities to the rover for the following day, and keep doing that again and again and again. Now there's a little problem with this, and if we actually compare a cycle of day and night on Earth, you can realize that at some point the human operators will have to work at different times of the day here. And that is because one day on Earth is actually 24 hours, as we know, but one day on Mars is actually almost 40 minutes longer than on Earth. And that's pretty tricky, because that means that if human operators want to keep working when it's nighttime on Mars, literally work on Mars time, they'll have to come into work on Earth 40 minutes later every single day. So they'll be basically trying to keep up with the time zone on Mars, which keeps shifting by 40 minutes every single day. So it's a big interplanetary jet lag that they're subject to. So during the very beginning of a Mars rover mission that just landed on Mars, they'll basically follow Mars time for about 3 months. But after that, they'll shift back to working on a regular schedule back on Earth, because it's really hard on the body to always come to work 40 minutes later every single day. I've never experienced it. I hope I will one day, but that's just what I've heard. It's really, really hard, apparently. So that caused also some other issues, because now when the rover is done during its work day on Mars, it'll communicate back to Earth. The humans will work together and then communicate back with the rover. But that's a good situation here, because the day and night cycles on Earth and Mars align very well together. But at some point later on, when the daytimes and night times coincide together, well, when the rovers are done working during the day on Mars, they'll send back the data they collected, but there'll be no one here to work because it's nighttime on the Earth. So then the humans will work the following day with that data, but that data won't really be useful. The list of activities they'll prepare won't really be useful, because that will coincide with the end of the following day on Mars. So then this data will only be useful the next day on Mars. So there's this one day in the middle where rovers won't be doing much activities. We'll call that a restricted sol. And that's one of the drawbacks of trying to operate a rover from Earth every single day. Also, a cool trivia fact is, in order to disambiguate, if they're saying, let's do that tomorrow, to make sure that people know that they mean maybe, Mars time tomorrow or Earth time tomorrow, they developed a new vocabulary for that. So one day on Mars, as I mentioned, is called one sol. If you want to mention today on Mars, you'll say to sol. If you want to say yesterday on Mars, you'll say yester sol, and so on. So that's some cool vocabulary that human operators will use every single day. Okay, let me take another sip of water. Systems on board rovers. So let's recap. We know how difficult the Martian environment is to deal with. We have prepared a list of commands that we've sent it to the rover, and now the rover has to accomplish these tasks. How does it do it? What are some of the tasks? What are some of the systems on board the rover that let it not only survive the Martian environment, but also drive around to collect all the images and the data that we need for the scientists back on Earth? Here's an artist rendering. This is the only artist render that I'll show during this presentation, because the Perseverance rover did return a lot of images, but I just found that this angle here was actually illustrated well what I wanted to show you guys and gals. So here are some of the systems that are crucial to getting the rover to navigate on Mars. So we have, the rover has 6 wheels, 4 of them on each corner, basically the 2 front wheels and the 2 back wheels. Not only can spin, but can also steer left and right. We have a suspension on board the rover that lets it adapt to different types of terrain. So it can, if there's some rocky, some rugged terrain, the suspension can adapt to it. Then we have an energy source, because we need power, we need electrical power to get the rover going and drive around. We have antennas, of course, to communicate with the rover. And then there are some cameras that will let the rover see around it, and some inertial sensors. Don't worry, if you've never heard of inertial sensors, I'll tell you what that means in a couple slides. And then we have the rover's onboard computer, which takes care of interpreting all the images that it takes and makes sure to keep the rover safe all the time. Here's an actual picture of the Perseverance rover that was taken about a month ago. And that's when the rover had deployed the little Mars helicopter on the Martian surface. So, I mentioned a bit earlier, and we've seen this on the previous picture, Curiosity's wheels sustained a lot of damage. And one of the reasons because of that, as I mentioned, is that the Martian surface where Curiosity is had these very sharp, pointy rocks. And as the rover was driving over them, some of the wheels were getting shoved into these rocks and punctured. And as the rover was driving on very rough terrain, these punctures were basically being stressed and big cracks would propagate across the wheels. And ever since, human operators were able to identify that and get the rover to avoid these very sharp, pointy rocks. But now that Perseverance has landed on Mars, we've learned from those lessons, and the wheels on board Perseverance are a lot more rugged, they're a little thicker, and they have a lot more grousers. And the grousers on them don't have any sharp corners where the stress can concentrate. They're just wavy grousers, and hopefully they'll work well. The rover's only been there for about 3 months. We'll see in a couple of months and a couple of years how it holds. When the rover has to turn, how does it do it? I've created those little animations with Ryan Kinnett's Rover 3D tool, which is a website I encourage every one of you to go and see. It lets you play with an actual realistic model of the Perseverance rover in an environment where the rover currently is on Mars, which is amazing. So the rover, to turn around, can actually turn all its 4 wheels to either drive along an arc, either left or right, like so. In this case, the rover is turning right. So the front 2 wheels are oriented in a way to turn right, and the rear back wheels are actually turning left to follow the same motion of the rover. And there are some mathematical algorithms that figure out exactly what angle to tell the wheels to steer at in order to get the rover to move around like that. The rover can also basically turn its wheels inward and do a point steer or a 0 radius steer. And that's also a very useful way to turn the rover around if we ever have to do it. So that's one of the benefits of having 4 wheel steering on board the rover. The rover also has this suspension. It's called a rocker-bogie suspension. And what it means is that there's this pivot point attaching to the body of the rover, and the front wheel is held together by the rocker part of the suspension. And right behind we have this little bogie part of the suspension, where the middle and the rear wheels are held together. And what's great about this suspension is that it can adapt to the environment very well. This is actually the top speed of the rover of Curiosity and Perseverance on Mars. That's something that not many people know. Their top speed is about 4.5 centimeters per second. It's not very fast, but the exploration of Mars is not a race either. So the rovers don't need to go very fast. So we see also a point steer that one of the test rovers was doing. But something a bit later on I wanted to show you is how the rover was driving over obstacles. One of the benefits of the rocker-bogie suspension is that it can climb over obstacles that are even more than 1 wheel diameter. And if you're driving over very rugged terrain, as you see here, the suspension can adapt to the different terrain configurations. Thanks to the rocker-bogie suspension, you can maintain all 6 wheels in contact with the ground or with an obstacle to maintain traction, and you keep the rover's weight as evenly distributed as possible. The top of the rover also has this bar here, and that's extremely useful. It's called a differential, and it's part of the rocker-bogie suspension. And what it does, look carefully at the geometry of the suspension. When one side of the wheels is going up, say the front left wheel goes up, the bar will pivot and make the other side of the suspension go down, and vice versa. So that if the rover ever climbs over one rock over its left wheel, say, then the right wheel will kind of compensate by pushing towards the ground and keep the rover's body as stable as possible. And that's extremely useful as well. So that's a very clever suspension design that's being used by rovers right now on Mars. It's called the rocker-bogie suspension. Now let's talk energy. So one of the the only energy source that the Curiosity rover and Perseverance are using is called, let me take a deep breath, multi-mission radioisotope thermoelectric generator, or MMRTG. That's a very complicated name, and don't be afraid by it. What essentially it does is there are these radioactive blocks of material, of plutonium actually, inside of the battery. And they're decaying slowly and they're generating a lot of heat. They're extremely hot. The outside environment of Mars, like I mentioned earlier, is extremely cold. And there's this little device called the thermocouple that basically will generate electricity when there are big differences in temperature. So we take advantage of the fact that this radioactive material is extremely hot and the outside environment on Mars is extremely cold to generate electrical power and charge the rover's batteries. And that's extremely useful because no matter if it's day or night, this MMRTG will work all the time and always fill up the batteries. The drawback though is that it becomes less and less efficient all the time, every year. So the rover will probably have enough electrical power to last for about 14 years. If you compare this with one of the previous missions, the Mars Exploration Rover missions, they were using solar panels. And where you're using solar panels, it's a more sustainable way to go about Mars exploration, and we'll probably see more solar-powered rovers in the future than rovers using an MMRTG. But you're at the mercy of the Martian dust, and you might get to a point where your rover solar panels are covered in dust, and you won't be receiving as much sunlight onto those panels to generate a lot of electricity. For example, this is the Opportunity rover. On that specific day of the mission, it generated about 353 watt-hours. That's a unit of how we quantify energy, of electrical energy that was converted from the sunlight that hit its solar panels. But a couple days later, there was a gust of wind that blew away the dust, and all of a sudden, the solar panels were generating a lot more electricity. And just for comparison, we generated a lot more electricity on that day. So you're at the mercy of the Martian dusty environment when you're using solar panels. All right, so Perseverance also uses antennas to communicate with Earth. Some of them can only communicate with the orbiter in orbit around Mars, like what we've mentioned, the orbiters with the big high-resolution cameras. Some of them can talk directly with Earth. And that's just mind-blowing because, you know, if you have say in your home you have a Wi-Fi router and you're having trouble to connect to it if it's in a different room, well, you know, tell yourself that NASA is able to communicate with a rover directly from Earth, which is pretty cool to think about. Okay, so let's talk autonomous navigation now. So we have the rover. It received all the commands it needs to accomplish. It has enough power to do it. And now it's time to drive autonomously on the surface of Mars. A lot of robots, even robots on Earth, will use these three main steps to go about it. The first one, we call that localization, or odometry. That might be a new word. You might not have heard that before, but essentially what it means is we're trying to estimate by how much the rover has moved. That's essentially what it is. You might have heard of an odometer, which is a sensor inside a car that tries to keep track of how much the car has moved since it was built. It's a bit the same thing here. We're trying to estimate by how much the rover has moved. So if the rover drives forward, we want to know how far it drove. If it climbed onto a rock, like our little rover here, we want to know by how much is it tilting to the left or right or pitching up or down. So that's what odometry is. Once we understand how the rover has moved, we have to look around for obstacles. So the rover will be able to identify rocks, basically big geometric obstacles like big rocks on the Martian surface, and make sure to try to avoid them by planning a trajectory that will avoid these rocks or these other obstacles, and then we'll repeat. We'll move, it'll try to localize itself, it'll try to look out for new obstacles, and keep going like that. These are the three main steps that a rover follows to navigate autonomously on Mars And these are some of the steps that a lot of robots, even robots on Earth, will follow to drive around by themselves even on Earth. So first, odometry. How does the rover estimate how much it moved? One of the things you can do is to do something similar to what cars are doing, and to count the number of turns that basically count the number of turns that your wheels made. And that's okay, but if the rover is ever driving on sand and it's very slippery, well, some of the wheels might be kind of spinning, but then the rover is getting stuck in sand and it's not really moving. So we want to make sure that the rover can realize that it's getting stuck in sand. So we'll use some other sensors to help it understand that. One of them is called an inertial. We can do inertial odometry. That's essentially using a sensor called an IMU. And IMU basically tells the rover how much it's tilting, left, right, forward, backwards. Can even detect how the rover is spinning around on itself. It's a little bit like if you're laying on the ground and you close your eyes, you can tell that you're laying on the ground because the gravity is kind of pulling you downwards. Even if you close your eyes and you turn around, say on the spinning chair or any other way, you'll also detect, even if you have your eyes closed, that you're spinning around because you feel the motion. The rover can also feel the same motion too with this instrument. So that's pretty useful when we drive around. The last thing we can do is to use the rover's cameras. So the rover can take a picture, move around, take another picture, and by comparing these two images, it can kind of try to estimate by how much it moved. It will try to guess by how much it moved, and that will be very useful to it. That's actually called visual odometry, and I have a little example here. So this is a series of images taken by the Curiosity rover when it was driving. And for us as humans, when we look at this, we intuitively can tell that the rover was driving forward, and at the very end it turned left. We can basically write algorithms and do some maths to tell the rover how to compute that by itself. Also, now, once we understood how to basically localize the rover and do odometry, we have to look out for obstacles around the rover. And one of the ways we can do this is, again, using the cameras. You might have noticed that a lot of cameras on board the rover so far, they come in pairs of two. On the rover's mast, we have navigation cameras. There's one on the left here, one on the right. On the belly of the rover, we have hazard avoidance cameras. These cameras look out for obstacles that are immediately in front of the rover. Some obstacles that might have been missed by the navigation cameras, or to help the rover do some other tasks. And they also come in pair. This camera here is paired up with this one, and that one here is paired up with that one. And by using two images, we can generate a big 3D environment around the rover. For example, here, this is an image taken on May 4th by the Curiosity rover, by the Perseverance rover. That's basically last week. That came from the left navigation camera, this one here. And here's, from the same point of view, the right camera image taken at the exact same time. That's this camera here. So you compare left camera, left, right. And we can combine these two images to generate a 3D environment of the terrain. Here are some examples of that. So here is basically a 3D environment generated with images from the Curiosity rover. On the right, this is another 3D environment generated back on Earth when human engineers were testing these cameras at NASA's Jet Propulsion Laboratory. What's cool on Perseverance is that the cameras have a very, very, very high resolution. It's about 20 megapixels, which is very high for a rover. So these 3D environments that are being generated with stereo vision have a very high resolution, and that's really, really nice. That's very useful. And lastly, once the rover can map its 3D environment and look out for geometric obstacles like big rocks, it can find a trajectory to go around them. What's cool with Perseverance is now it can straddle basically different obstacles. So it knows how much space each of its wheels will take, and it can drive around these obstacles in a nicer way than previous rovers. back then, with the Curiosity rover, using autonomous navigation was actually very slow. So humans didn't really use them. They would just tell the rover exactly what to do because it would be much, much quicker. Here's an example of that here. So at first the rover was driving forward, and it was just basically following blindly the instructions that the human operators told it to do. And then it started driving autonomously, and it did exactly what we talked about. It localized itself, it looked out for obstacles, and it moved. And this is what it looks like. So the rover will move, look out for obstacles, localize itself, look out for obstacles, move, and so on. It does these 3 steps until it reached the navigation goal that humans wanted it to reach. And before closing the presentation, I just wanted to take about 3 minutes to talk about what's next on when it comes to robotic navigation on Mars. So we've talked about the Perseverance rover that landed on Mars about 3 months ago, and it landed at this location called Jezero Crater. And what is so special about Jezero Crater is that we think that back then, a couple billion years ago, when Mars was very young, it had liquid water on its surface, and Jezero Crater was actually hosting a lake. And it's not a lake that was just still like that. There was a river flowing into the lake, and there was an outflow channel letting the water leave the lake. So there was a continuous flow of water in Jezero Crater. And this basically brought sediments inside of the crater. If we zoom in on that spot, what it looks like today, of course there are no water anymore, it all dried out. But this is a very nice place that rovers can explore and hopefully look for, if there was life early on in the Martian history, we can probably detect some signs of this ancient life in that location. Right now, the rover landed around here and out of the frame and is making its way up towards this big formation called the delta that was basically all the sediments that were deposited by the river flowing into the Jezero Lake a very long time ago. And lastly, there's a mission I want to talk about because Science Odyssey is a Canadian festival, and I want to talk about the biggest Canadian contribution so far to Martian robotic exploration. It's the ExoMars Program, and that's a European Space Agency mission that was put together. Mostly it's a collaboration between the European Space Agency and the Russian Space Agency. But all of the locomotion system of the rover for that mission, rover is called Rosalind Franklin, named after a very famous British chemist in the early to mid 1900s. Basically this rover's suspension, locomotion, wheels, and everything, the whole drive system was designed in Canada. So this is, I think, by far the biggest contribution of Canada to Martian robotic exploration, and that's something to be very excited about in Canada. And that mission should take off from Earth towards Mars in 2022. So hopefully we'll hear more about that mission a little bit. I got the chance to work on that rover back in 2016 as an intern for a couple months, and it was just a blast, and I really hope it lands there safely on Mars. And that's pretty much it for my presentation. So before looking at the questions in the chat, if there are any, I just wanted to thank you for coming here and taking some time off of your evening or afternoon or wherever, whatever the time is where you're looking at this presentation from. If you have any, again, questions, write them in the chat. I'll get to them in a minute. If you have any feedback about this presentation, things that you liked, or some ideas you have in how we can improve the quality of those presentations, let us know as well in the chat or in the comment section below. And if you ever want to hear more of like some presentations like that, if you have some ideas or something that I kind of touch up on today as part of that presentation, I purposefully kept everything very high level to maximize the reach to a wide audience and hopefully get you excited about Martian exploration and learn more about it. But if you have some ideas on some topics for some future presentations, maybe you want us to do a deeper technical dive into some topic, let us know as well in the comments. And yeah, if you want to connect with me, the best way to do it would be on social media. either on LinkedIn or on Twitter. My handle is @olamarre in both locations. If you want to learn more about some of the research that I'm doing at the University of Toronto, you can visit the website of my laboratory, the STARS Lab, so starslab.ca. Also connect with us as well on our social media pages. So that's it. So it's where there's not much feedback with the audience right now when we do these presentations, but I'll look at the if there are any questions here. Okay, so there's our first question. Thanks, Olivier. You're welcome. How do Perseverance and Ingenuity determine their position on Mars? So they're definitely not using GPS, as you pointed out. There's no GPS satellite network yet on Mars. So the way they're doing it is basically, I talked about how they can use, I'll go back to the slide and I'll just briefly re-mention it. I'm not sure when exactly you asked the question. It might have been before I talked about that. But the rover can either use its wheels, it can also use its a sensor inside of it that tells it by how much it's tilting and how much it's spinned on itself, called an IMU. It can also use its cameras. But all these sensors are, they give you just so much accuracy that you also need humans right now to tell them exactly, to basically determine where they are exactly on the Martian surface. There's no system, there's no way to give these rovers a big orbital map of where they are and let them figure it out on their own. They need to have the help of humans to tell them exactly where they are on the Martian surface and where to head next in the following days. As to how Ingenuity does it, I didn't talk much about Ingenuity, which is the Mars helicopter. Let me just pull a quick picture of that, of this helicopter. So here's a more close-up picture of the Mars helicopter. The helicopter itself did a couple flights already, and it was the very first actively controlled aircraft on the surface of another planet, and was a very huge success. The way the helicopter is localizing itself, I think it's also using inertial sensing, like the IMU I talked about earlier. It also has a camera that looks downwards at the ground. And when the helicopter moves, it can also estimate from imagery by how much it moved. Also use visual odometry, basically. And it also has an altimeter, I think. And that basically tells the helicopter how high it is above the ground. So it can use all of this information to estimate exactly where it is above the ground and keep it safe. Hopefully that answers your question. So Zayad, hey Zayad, is asking, the color stripe from high rise, is that by design or is that a bug? No, it's actually by design. It's not a bug. That'll be it'll be a pretty funny, or depending how you see it. It's not a bug. It's by design. I'm not sure why they did not extend color imagery to the whole span of the image. Probably because these images take a lot, like they're very huge. Like I think this image here was 24 gigabytes in size. For a spacecraft in orbit around Mars, this is huge. That's a lot of data it has to send back to Earth. And I think they're only basically to get color imagery, you need to have 3 different types of sensors, like red, green, blue. And there are only these 3 channels are at the center of the sensor, of the high-rise sensor. All the other ones are only red channels. So they only can capture 1 channel. And I think that's in an effort to keep the data size to a minimum. If you want to capture one specific area in color, you just make sure you center the camera over the region you want to image in color. But the stripe here, it looks pretty small on that image, but it's actually pretty wide. So it's enough for our needs right now. So from Hallie, he's here, how fast does the rover move on average? That's a very good question. And the top speed of the rover is about 4.6 centimeters per second. So I'm not sure like how often they'll drive it to its top speed. It's already pretty slow, so I'm pretty sure they'll drive it to 4.6 centimeters per second, the top speed most of the time. But there might be instances, for example, where they have to, whenever they have to deploy the robotic arm on the rover. Let me show you a picture back of what the rover looks like. No, that's not a good picture. All right, this one here. So the rover has this robotic arm. Sometimes to get closer to a specific target of interest, they'll basically they'll just make the rover kind of inch forward just a little bit. And in that case, it might be driving a little slowly. But I think most of the time, whenever they have to drive over several meters, they'll drive to top speed, which is about 4.6 centimeters per second. Call the Auto Club, yeah. The navigation, okay, so the navigation goals, are those absolute coordinates on a map or relative positions compared to the current position? So right now there are just relative position relative to the rover. Back on Earth, human operators, everything is absolute on a reference base map, like the one we looked at earlier. But to from the rover's perspective, we give it waypoints from its current location. There's a whole system of reference frames. I think most of the time it's with respect to the rover's current location, but there's a whole hierarchy of different reference frames that human operators will use to keep track of where exactly the rover is. So what region it's in, and transform from that region to the big base map. So you have a base map, you have site frames, you have rover frames, you have waypoints. So there's a whole hierarchy. But as far as the rover is concerned, I'm pretty sure it's with respect to its current location on the Martian surface. In what ways do the trade-offs between simplicity, reliability, and efficiency affects the state estimation systems of the rover? Are they optimization-based, filter-based, and can they use AI? So right now, most of the computation used on board rovers is they do it using conventional robotics and algorithms. So more filtering-based systems, say for the IMU, so the inertial sensor. I'm pretty sure they're using conventional filtering. There's also a lot of proprietary information on that end because they're using military, for some of the instruments on board the rover, they're using military instrumentation. So they don't really publish out exactly, for example, with the IMU, how they filter the data out. But for now, there's no neural net or any form of advanced artificial intelligence used to help the rover navigate around. And that's simply because the computers on board the rover are extremely limited in terms of computational power. They're designed to survive the harsh Martian environment and the intense radiations for a long period of time. There's a system, though, on board the rover to help it target look at scientifically interesting rocks. And it's a system called Aegis, AEGIS, and the rover can basically extract features using basic computer vision and I think some form of machine learning to extract some features on the ground and take pictures of it. But these images are only used this data is only used for scientific observations. It's not really used yet for navigation. If you're curious about machine learning on planetary navigation, one of the persons that I worked with at NASA JPL, his name is Masahiro Ono, his team worked on setting up a neural network which would classify different terrain types. And as part of the extended mission of the Perseverance rover, there are plans to uplink a very light version of this neural net to run it on the rover. And this would be the very first neural net running on board a rover. So if everything goes well, we might see Perseverance running a very light version of a neural net, classifying the terrain types that it sees and help it in with its navigation. So Leo asks, were any lessons learned from the earlier rovers in regard to control from Earth? So let me think about that. So I'm trying to think about some of the issues that came up with the previous missions. I'm pretty sure. So everything that's being done on the rover right now is built on experience that was collected with previous missions. One of them is, for example, with Perseverance. Or let me show you a picture of Curiosity. Okay, so that picture here. So one of the things that they've learned to do, well, in the case of Curiosity, is to avoid sharp rocks, but also they've uploaded a patch to the software they use for navigation planning in order to reduce the amount of wheel damage. And if we go into the details of how wheel damage was occurring, is that the front wheels sustained the most damage. And the way that worked was that the front wheels, whenever they would hit an obstacle, in the unfortunate case, sometimes it might be very sharp obstacles, they would basically keep turning at the same rate as all the other wheels. But as they would start climbing on a rock and you have all the other wheels pushing on it, they would skid on these very sharp rocks, and that's what would cause the punctures inside the wheels. So one of the things that they did is to adjust the wheel spin rotation whenever they detect on the bogie angles that they start changing because the wheel is starting to climb on an obstacle. They'll slow down the rate of rotation of all the other wheels so that the wheel that's climbing on these obstacles does not skid as much. So that's one of the ways they've kept the rover safe, and I'm pretty sure the same thing is being done on board Perseverance. In the case of, I'm pretty sure there are also some lessons learned when it comes to solar powered management. So I talked a little bit about solar power. So the Mars exploration rovers had solar panels, like I mentioned, and they had to basically, the initial mission was only supposed to last about 3 months. And they figured out a way to drive these rovers around for one of these rovers at least for 14 years. The other one, Spirit, actually lasted, I think, 7 years. So that's still a lot. So they had to find ways to manage the solar power generation on board these rovers. And that means that whenever it was winter where these rovers were on the Martian surface, they had to basically find terrain that was oriented towards the sun as much as possible to make sure that the rovers keep the right amount of energy to keep their heaters on and make sure that the rovers don't freeze during the night and basically die from freezing too much. So I'm pretty sure we'll see future solar-powered rover missions reuse a lot of lessons learned with this mission here. So yeah, I don't have, I wish I could tell you more. Nothing comes to mind right now. If I think about something, I'll let you know. So what kind of software development was done to train the rover? Was machine learning involved? So going back a little bit to what I mentioned, I'm not going to repeat it, but machine learning was not really involved so far to train the rovers. They are using mostly conventional robotics processes to drive around on Mars, but they will do a lot of hardware testing and to develop their procedures to make sure that the rovers stay safe on Mars. And one of the things they'll do is, for example, for every rover on Mars, there's an engineering copy of that rover on Earth that they can use for testing. In the case of Curiosity and Perseverance, there's also this mobility test bed called Scarecrow. And this is just aimed at testing the mobility system of these rovers on Earth. And the rover itself weighs about 1/3 of what the rover weighs, to sort of kind of simulate as if it was in Martian environment, the weight it would have in Martian environments. So they'll do a lot of hardware testing and procedures to make sure that these rovers stay safe. But from a machine learning perspective and algorithms, there's a lot of simulations on Earth, but a lot of it is backed by hardware tests on Earth. So there's not much training for machine learning algorithms yet happening in onboard planetary rovers, but hopefully in the future there will. So what would happen if the rover ran out of power randomly and could not go anywhere? That would be a really bad day. So you don't want that to happen. So actually the Opportunity rover, one of the solar powered rovers, actually died because of a global dust storm. there was these big global dust storms that basically arise whenever Mars on its orbit around the sun gets close to it. Mars' orbit is very eccentric, and whenever it's far away from it, everything is calm. But as Mars comes back towards Earth on its towards the sun on its orbit, the atmosphere heats up. Some of the ice and carbon dioxide at the poles melts a little bit, thickens the atmosphere, and it causes a lot stronger winds, and then the dust just picks up. And once in a while you'll have global dust storms, and one of them happened to Opportunity. If that ever happens, unfortunately your rover will likely die because the Martian nights are extremely cold. Typically, rovers, if they ever experience some sort of failure, they have different failure modes they can go into to stay as safe as possible. So if the rover ever has some sort of readings in its telemetry that's off from what it should expect, for example, when it's driving, it'll just stop and enter in safe mode and wait for additional instructions from Earth. So JPL, the engineers working and operators working on that, what they're very good at is all the what ifs. What if that happened? What if this happens? They have a whole list of different scenarios that can happen to the rover, and they try to make sure they capture everything that could happen to these rovers to make sure that this does not happen. But if power was to cut and was not to be restored very shortly, I don't think these rovers could survive a Martian night, unfortunately. Good question. Would it be better if we have both solar panels and plutonium batteries to charge the rover? That's a very good question. I'm sure there are some mission concepts that were studied that look at mixing both together. The thing is, if you use a plutonium, a radioactive battery, before, for Curiosity, you needed presidential approval, literally, to approve the construction of that. Because you're literally using plutonium, which can be used for warfare. It's very dangerous. And now I think you don't need presidential approval, but you still need a very high approval for that. And it's not very sustainable. If we want a future where we're using several rovers, like hundreds of rovers on the moon and even on Mars, I don't think we should rely on basically radioactive batteries. I think these batteries will still be needed though if you want to explore further into the solar system. Say you send a probe near one of the big gas giants, whether it's Saturn or Uranus, Neptune, Pluto. At that point, the sun is so dim that I don't think you'd be able to generate enough power, at least for the current spacecraft systems we have, to have the spacecraft survive to the cold of space. But when it comes to navigating on Mars or on the moon, I think you could get away with solar-powered rovers, and that's a lot more scalable. But there might be a mission where having both might make sense. So yeah, that's a good point. So I think that was all the questions, and it's pretty much 8:35, so I think we'll call up the event here. So again, thank you so much for attending. I hope you enjoyed it. If there's some things that I said that were off, feel free to write in the comments below and correct me. I'd be really appreciated. And yeah, just leave us some feedback, how you like that presentation. If you'd like to see more of this, maybe you'd like us to dive a little bit deeper on give a more technical presentation on some aspects of planetary navigation that could be interesting. So yeah, let us know. And thanks again for attending. Bye.